World demand for energy, chemicals, materials and products is increasing every year. Current production systems and consumption patterns are unsustainable. And so the global challenge is to meet demand through increasingly sustainable sources. To this end, we believe biomass has a unique role to play. Biomass is a sustainable source of resources that can be pre-treated, converted, and refined to produce fuel, chemicals for product manufacture, heat, and electricity. The benefits of harnessing biomass are immense. For a start, it will invigorate farming and rural communities. It will reduce CO2 emissions from fossil fuels. It will encourage biodiversity and sustainability, and will improve the security of energy and fuel supplies. Under the biomass umbrella is a wide array of organic sources, including willow, straw, miscanthus grass, residue from forest management, and even the byproducts of manufacturing such as food or sawmill waste. These sources can be harvested by felling, chipping, combine harvesting, cutting, and clearance. Once harvested, they need transporting to where they can be pre-treated. There are two main routes when it comes to processing biomass, either biological or thermochemical. These processes are at the core of the Biosynergy project, which the European Commission has sponsored. The biological process firstly involves pre-treatment, in which the biomass is received, handled, stored, dried and reduced in size. Next, hemicellulose and cellulose are converted by a process of hydrolysis using acid or enzymes. This creates sugars, which are fermented to produce a dilute product from which ethanol is separated. The ethanol produced can then be used as a fuel in its own right, a fuel additive, an industrial solvent, or processed as a petrochemical to produce other specialty and commodity chemicals, which can be used to make a wide range of consumer products. A byproduct of hydrolysis is lignin, which is used in the production of transport fuels and specialty and commodity chemicals. The thermochemical processing is different in that high temperatures are involved, but again involves pre-treatment in which the biomass is received, handled, stored, dried, and reduced in size. It then goes through one of three different types of thermochemical processing: combustion, gasification, or pyrolysis. Combustion is used to generate heat, which produces steam, and this in turn drives turbines to generate power. Gasification turns biomass into fuel gas or synthesis gas. Fuel gas is used to generate power and heating, while synthesis gas is used to manufacture synthetic transport fuels and bulk chemicals, which can then be refined to produce specialty chemicals, chemicals such as polymers used in the manufacture of consumer goods. Pyrolysis encompasses a number of varying processes. Fast pyrolysis produces high yields of a high-energy liquid that is cost-efficient to handle and transport. This can be used directly for heat and power, or to produce chemicals such as adhesive resins for wood panels. It can also be processed further by gasification. Low-temperature pyrolysis, or torrefaction, also prepares biomass for gasification and improves its quality. Various other forms of pyrolysis, intermediate and slow pyrolysis, also produce gas liquids and solid that can be used in analogous applications such as acetic acid. So, what do these conversion and upgrading processes actually produce? For a start, they produce heat and power, either for industrial and domestic use, or for use in the biomass conversion and upgrading processes. Secondly, they produce transport fuels, either by blending bioethanol with fuel, or using it as a fuel in its own right, or by using hydrocarbons to produce synthetic diesel and gasoline, Thirdly, they produce specialty and commodity chemicals which can be used to manufacture a wide range of products for use in industry and ultimately in consumer goods. It's essential, of course, that we get the most effective output from processing biomass. And to achieve this, we need to look at integrating the biomass processes in order to optimize the range of products they generate. In essence, this means developing integrated biorefineries capable of producing a similar range of products to those produced by conventional petrochemical refineries. The concepts we develop for biorefineries also need to be as cost competitive as possible, and this can be achieved by using as much of the biomass as possible. One aim is a design for an integrated lignocellulose biorefinery based on the straw-based bioethanol demonstration plant of Abengoa Bioenergy in Salamanca, Spain. An example is provided in this diagram. At present, we are evaluating 5 different methods of straw pre-treatment for the production of fermentable sugars, each differing in performance and cost. The optimal process will depend on the processing destination of the fractions and the envisaged end products. As well as producing ethanol by fermentation, we are also investigating other biochemical processes that produce acetone, butanol, and other platform chemicals. Another idea is the development of thermochemical conversion integrated with separation technologies. For example, thermal conversion by gasification produces synthesis gas, which can be converted into ethanol, methanol, diesel, and gasoline. Thermal conversion by pyrolysis produces a liquid oil, which can be used as an energy carrier that can be upgraded into refinery feedstock material for the production of transport fuels, and can be used as a source of commodity and specialty chemicals. A key byproduct from bioethanol production is lignin, and we are investigating this as a feedstock for resins and phenol for polymer synthesis, while potential chemicals from the hemicellulose fraction include surfactants and furfural. At present, we are evaluating all these process concepts in order to identify the most promising biorefinery chains in terms of performance, energy efficiency, environmental performance, cost, and socio-economic contributions. This will entail several of the best performing biorefinery processes being tested at pilot plant scale. It all sounds workable, but there are a number of challenges ahead if we are to seriously consider biomass as a sustainable energy source for the future. For example, where do we source biomass without damaging local economies and areas set aside for food production and feedstock? How do we reduce processing costs? And how do we integrate products into the supply chain and get them to consumers? How do we go about producing multiple products, making the whole process more cost efficient? And what is the overall life cycle impact, taking into account use of land, cost of processing, the carbon footprint, and the socio-economic benefits? These are the challenges Biosynergy needs to overcome if we are to optimize the range of products that can be derived from a biorefinery and provide future generations with a viable and sustainable biomass resource. The Biosynergy Consortium consists of 17 complementary partners with a high level of industrial participation. There are 3 companies, 8 research institutes, 2 universities, and 4 SMEs. Each is a market leader in their respective fields of innovative technology development and implementation. Biosynergy has a total budget of €13.4 million, an EU grant of €7 million, and is coordinated by the Energy Research Centre of the Netherlands.